I did tell you guys the first day of school, I do a lot of things that are, I don't know, unorthodox as a teacher. You'll discover that. I like to think outside the box and do things differently. I'm not a big believer of like, everyone does it this way, so let's do it this way. And sometimes that's good, but sometimes that's a challenge, right? Like writing a multiple choice test where you can start losing marks, that's going to change your thinking. But I hope you get it. I hope it changes your thinking for the better, right? I hope it's going to push you to become smarter and stronger students rather than kids who just pick C because you were told to do that in junior high. Because you were probably told that, right? I don't want, you guys know what lemmings are, right? You ever heard of those before? Like lemmings will like literally follow each other off the cliff. Like if one of them falls off, they just keep following. Ever heard of this before? Right. I don't want to train you guys like that. I want to give you critical thinking skills. That's way more important. So, okay, let's talk through these notes. One of the things I need you guys to be able to do is understand just some basic properties of compounds. So, so far we've talked about the idea of how like chemistry is learning another language. So if I were to ask you what the letters are, you'd say, well, letters are like periodic table elements, right? And then one of the days we spent recently, we talked about doing words. Like, for example, if I were to give you this guy right here, NaCl, you guys would be able to call it? Good. Okay, awesome, right? And hopefully you're getting faster at that so that if I said you had AuCl3, I'll write it out. AuCl3, you'd know it was? Gold 3 chloride. Roman numeral, but close. Okay. Gold has more than one valence. That's all. Okay. One of the things I'd like you to know about that then is kind of like with, if this was a word, I need you to know not just what the name of the word is. So like my daughter is kind of starting to learn how to read, right? And if she looks at the word and says, oh, that word is dog, that's great. But if she doesn't know what a dog is, how is that helpful? Does that make sense? She needs to know that a dog is something that she can pet and that's going to eat dog food and that's going to bark, right? Those are all properties of a dog. A dog is hairy, a dog barks, right? Same thing here. I want to talk about some of the properties that something like AuCl3 would have. So most of these are things where honestly I would just write them down in your data booklet if you can't memorize them. Because you guys can write anything in there you want. So first thing about ionic compounds you guys need to know. Ionic things have a very high melting point. What does that mean? Well, it means that they are usually solid. That's what a high melting point means. Like, think about what melting means. Melting means to take something and turn it from a solid into a liquid. What is the melting point of water? 0, yeah, right? That's when ice turns into liquid. What would the melting point of this table be? Not 0. Because otherwise stuff would literally be melting in front of us, right? So typically what that means is that at room temperature, if something is ionic and it has a very high melting point, it's probably solid. And if we add heat to it, eventually we can cause it to melt down, right? Like think of like a metal. If I had like molten iron, I might need to get it to 5,000 degrees Celsius, and I can make iron into like liquid, right? And then I can like reform it into new shapes in a mold. Does that make sense? So ionic things are usually solid, and the reason for it is due to alternating positive and negative charges. Okay. You know how like sodium is a plus charge and chlorine is a minus charge? Well, the way these things stick together, that's actually a very strong shape. It's kind of like magnets. You have a magnet, another magnet, and they stick together, and then another magnet, and they stick together, and you keep interlocking them in a shape like this. Very strong shape. Okay. Similar to that, although you can break them in half, usually they don't shatter. That's probably a word I would use. Okay. Let's say that I had like a molecule here, like a chunk of solid, and I found a way to somehow cleave it in half. This side and this side would still stick together. Does that make sense? It wouldn't just like all just decompose. Okay. Long story short, most of these things have a lot of strength in their bonds. Ionic things are fairly strong bonds. However, there is one way of breaking an ionic bond, and it involves adding it to water. Okay. We're going to do lots and lots of labs. Have you guys done anything like that before, though, like working with chemicals? Did you do anything like that in grade 10? Okay. I guess in lieu of you guys not having done a lot of lab work, imagine that you're making Kool-Aid and you're using like Kool-Aid crystals. You know how they're solid? And then you pour them into water and you stir them all up. Well, what happens to those Kool-Aid crystals? They dissolve. That's a good word to use, yeah. We have a term for that. In chemistry, soluble means that they dissolve. So, long story short, the structural integrity of ionic things, yes, is very strong. However, it is actually possible to break up this structural integrity by adding it to water. And the reason why is that water is a polar substance. Have you ever heard that term before? If you haven't, don't worry about it. It's not really the most important thing. But long story short is water has the ability to pull apart ionic compounds. So yes, ionic compounds are structurally strong, but not in water. Water actually can dissolve things. You guys probably know this from more than just Kool-Aid, right? Like if you stir something into water, you can probably get it to disappear. It doesn't actually disappear, it just dissolves. Have you guys ever seen a chart like this before? Ever worked with this? There's one in your data booklet on maybe like the 4th page in. So I'm trying to find it for you here. 1, 2, 3, 4. Page 6. There's a chart on here. And this chart basically is a way of letting you know how well things dissolve. It's a 3-column chart. The one I have up here is not the exact same as yours, but it's kind of close. Do you guys know how to use this chart? You want to be brave and explain to me? Okay, I'll do it. Okay, so here's how this chart works. If something is considered to be very soluble, it means yes, it does dissolve. Okay. If something is considered to be slightly soluble, it means no, it doesn't really dissolve at all. So maybe it dissolves a little bit, but it doesn't really dissolve very well. So often what we do is for a state of matter, we write AQ after things that are very soluble. You guys seen that before? What it stands for? Aqueous, yeah. AQ for aqueous means that like aqua, like probably Latin for water. It means that it will dissolve in water. Okay. If something falls into the bottom category, usually we write that it's still solid because it hasn't broken up into pieces. Okay. So then here's how this chart works. Let's say I give you a compound like, say, NaCl. Okay. What you want to do is you want to look along the top for one of the ions that's up there. For example, here's Cl. That is the anion of the NaCl I'm working with. Okay. Will NaCl dissolve in water? Do you guys know the answer to this? If you put salt in water, will it dissolve? Okay, so that means what should happen is that it should be in the top category. And see how it says most right here? That means that most everything with chlorine is going to dissolve. However, there are some exceptions. For example, if we had lead chloride would be solid because it's one of the exceptions. Does that make sense? Let's do another one. Just erase some of this. Let's do calcium carbonate, CaCO3. So in order to use this table, what I'd suggest is look for either the calcium or look for the carbonate up top. Either should work. Most of the things in the table are usually the anions. So I'd look for carbonate, which is right here. That works so far? So then looking in the column here, these guys right here, including carbonate, only dissolve with things in group 1. So that's like sodium, lithium, potassium, rubidium. Does that make sense how it's in group 1 there? Is calcium in group 1? What group is calcium in? Okay, so that doesn't help. Or if it's ammonia, or ammonium, sorry, which it's not. So therefore, calcium must be down here in the most column. So therefore, I would expect calcium carbonate to not really dissolve in water. Is that something you guys have seen before? Okay. Okay, on other properties, because of the fact that ionic things get pulled apart in water, what ends up happening is you often get negative and positive charges no longer clumped together in solid format, but in a separated format. And one of the cool things about this is that they can conduct electricity. So similar to when you guys were wanting to put a piece of metal in the light socket, you guys intuitively knew that if it was wet, it conducts electricity. That's actually one of the reasons why, is that water is often a very good conductor of electricity if there's some sort of ions inside of it. So it makes it dangerous, actually. Okay, the opposite of ionic compounds is molecular compounds. And pretty much across the board, molecular compounds have the exact opposite properties of ionic things. Like, it's not exactly opposite in every case, but for the most part, they are opposites. Okay? For example, they have low melting points. So again, if you have a high melting point, it probably means that you're going to be a solid. Lots of structural strength to you. I can't put my hand through a solid. Okay? However, here's a good example of a molecular compound, CO2, carbon dioxide. I can move carbon dioxide around. It does not have a lot of strength to it. Here's a carbon dioxide molecule right here. Here's a carbon dioxide molecule right here. Is there a lot of strength of attraction between those molecules as their state of matter? No. That's why these things are usually gases. Maybe they're liquids, like for example, water is often a liquid. But chances are, if it's ionic, it's probably solid. If it's covalent, molecular, whatever you want to call that, it's probably a liquid or a gas. Okay. There's just nowhere near as much strength between the molecules. And one of the biggest reasons why is that these things right here, they don't have positives and negatives. You know how ionic things are a metal and a non-metal? That's a lot of strength to it. It's like that magnet concept of like how they're going to stick together. When you have to share your electrons, like covalent things do, I mean, it works. Don't get me wrong, it works, but there's nowhere near as much strength to it. Okay. Hence, they're very weak. For example, like a snowflake would be a good example. Can I get water to stick to other water? Sure, like I can make snowflakes. But is it like the most structurally strong thing in the world? A snowflake lands on my hand, it'll probably be gone within 10 seconds, right? I don't even have to do anything to it. All I need to do is have a little bit of body heat from my hand, and the snowflake will fall apart into water. Does that make sense? So these things are usually not very strong. You can break them apart fairly easily. Okay. Most of the time, the term we use is electrolytes. If something conducts, it's an electrolyte. If something doesn't conduct, it's a non-electrolyte. Have I introduced the word electrolytes to you guys before? You probably heard the word electrolytes if you're an athlete and you drink Gatorade or Powerade. You ever heard that before, where it's like, it's full of electrolytes? Electrolytes are basically ions that allow electricity to conduct from a chemistry point of view, which is kind of weird that you'd want that in your energy drinks, but I mean, that's basically what it's referring to, is its ability to conduct. It provides a lot of ions. If you ever actually look at like the side of a like a container, this one might have, no, this one won't even have it. Often they'll list all of the different dissolved ions, like sodiums and lithiums and carbonates, and those are useful to your body, basically. So, anyways, these things do not conduct because, again, they don't have positive and negative components to it. NaCl has a positive and a negative. That allows for electricity to flow through. If it's just pure water by itself, probably won't. That being said, like most water that we actually have, like even tap water does have dissolved ions inside of it. Do you guys know this? Like if you have a well water often will have like, you know, chlorine, iron maybe inside of it. So when we work in the lab, I have to go buy something called distilled water. Basically, distilled water is just water, nothing else inside of it. Like there's no dissolved chlorine and sodium ions, it's just pure. Okay? And that will hopefully not conduct at all, actually. We'll actually do a lab on this later. Okay. I've got a picture here of some apparatus that we would use when we actually get to a lab. Usually what we do is we just hook up a little light bulb, and you stick a couple of electrodes in water, or whatever the solution is, and if the light bulb lights up, then it conducts, and if the light bulb doesn't light up, then it doesn't conduct. Does that make sense? All right, moving on. One last property, then, of some compounds I want to talk about. There are certain compounds that have the property of being acidic or basic. You guys probably know those words, right? Like acids are usually considered to be fairly dangerous. Bases, although maybe in your mind you don't think of bases as being dangerous, they are just as dangerous actually too. We have properties I want you to know as well as a naming scheme. Okay, so here's what I want you to know so far. If it's an acid, it's able to have hydrogen in it. For example, like HCl, because it starts with an H, it's an acid. It's actually not the best definition of acids, but it works for where we're at right now. So here's some properties I hope you guys know. Acids conduct. They should dissolve in water. Here's probably the biggest one. We use litmus paper. You guys seen litmus paper before? Lab at least do a litmus paper test. Okay, so if it changes red in litmus paper, it's an acid. And if it turns blue, it's a base. Okay. Acidic things usually taste sour. For example, the most common example of this would be like a citrus acid. Like if you're having a grapefruit. Grapefruit is very sour, right? One of the reasons why is there's a fairly large acid content to it. Bases are basically like kind of the flip sides of acids. They taste bitter usually. They usually still conduct electricity, but they turn it blue if you're going to use litmus paper. We will do a lab on this so you can actually do some tangible hands-on stuff. Let's see how close I can go. Bases are defined by hydroxide ions. If it's something that ends in an OH, it ends up being a base. And we're going to cover this a lot in our first unit. But if an acid is an H and an OH is a base, anybody know what happens when you combine acid and base? And that makes it water, actually. H and OH combined together makes H2O. We kind of write it differently, but you have two H's and an O. So therefore, if you take an acid and you take a base, it becomes neutral. Water is neutral. Does that make sense? You guys ever seen that before or heard that before? No. So I need you guys to know some basic properties of them, but probably the most important takeaway here is that we have special ways of naming acids. We don't actually have special ways of naming bases, but we do for acids. Okay. So here are some of the naming rules. I have a chart on the next slide after this one here, and I'd recommend maybe kind of writing it down somewhere if you can't remember. So here's the way it works. Let's say that it's a hydrogen-containing compound, and you would have named it like this, hydrogen chloride. Its acid name then is hydrochloric acid. So if it's like a hydrogen ending in "ide," it becomes a hydro-something-ic acid. These guys right here are almost always binary compounds, like HCl, HF, HBr. So like this would be hydrogen chloride, call it hydrochloric acid. This would be hydrogen fluoride, call it hydrofluoric acid. This would be hydrogen bromide, call it hydrobromic acid. Does that make sense? These ones are very distinguishable because there's only ever like two parts to it. HI is hydroiodic acid. Actually, those are the only four I actually know of that really fit this naming scheme. Most of the acids we work with involve polyatomics, like say this guy right here, HNO3. NO3 is called a nitrate. So if we were to name it, we'd call it hydrogen nitrate. The way it works then, if it's a polyatomic, is we don't put a hydro in front anymore. We just call it something-ic acid. So like a hydrogen nitrate becomes nitric acid. Okay. Let me do another example here. Here's H2SO4. What is SO4 called? Sulfate. So we call it sulfuric acid. Does that make sense? Here, HBO3. What is a BO3? Not BO3. BO3 is one of the polyatomics. You have to look at the, like in your periodic table, you'll have to look in that top chart there. Find BO3. Borate. Okay. So if it's HBO3, it would be then boric acid. Eights turn into ics. I was once told a mnemonic to try to remember that, and it was that when you ate something that was very icky. Maybe that helps. Okay. The same rules then work if it's like a per something ate. So like, for example, let's say you have a perchlorate. Well, then it becomes a perchloric acid. So eights turn into ics. And if there was a per on the word, just leave a per in front of the acid, that's all. So if you had hydrogen perchlorate, it's perchloric acid. The other possibilities are the ites, like chlorite or sulfite or nitrite. Okay. The way those work is that ites turn into us. And the way I have to remember this one myself is that when you get into a fight, and someone punches you, especially in the stomach, you say, ugh. That's how I remember it. Fights make you go, ugh. So if this was a chlorite, you would call it chlorous acid. Or if this is a hypochlorite, you call it hypochlorous acid. You guys heard these before?
Yes.
I would say that most kids, it's not uncommon to like try to write down some basic rules in your data booklet so you can remember it. Like, feel free. Okay. Probably said this quote before. I'll say it many times. Einstein once said, "Never memorize things you can look up in books." This is one of those things where it's like, in 5 years after you do this lots like I do, you'll probably memorize it. But if you need to look it up, feel free, look it up. Okay. So write it down somewhere, but make sure you know how to name acids. So I have a whole bunch of examples still here. If you have a hydrogen nitrate, 8s turn into X. If it's hydrogen bromide, ides become hydrobromic acids. And same thing on the last slide, but you guys can read. I'm not a big believer in reading up things that you guys can read. Does that make sense? Okay, bases don't have weird naming rules. The reason why is that bases always end in OH. So whenever you have a base, it should always end with the word hydroxide. Calcium hydroxide is the base. Sodium hydroxide is the base. Does that make sense? If the last word you say is hydroxide, it's a base. So we don't have anything special for bases. But acids, there's the 5 types. The hydro something acid, which usually means hydrogen is attached to one of these guys. The per-8 and the 8s, which become X, and the us's and the ites and the hypoites, which become us's. If you remember that, you're good. All right. Any questions, comments, concerns, conundrums, curiosities, complaints, criticisms? Is this still a review for you guys?
Yeah.
Okay, cool. Okay, go take a 5-minute break. When you come back, you get the next hour or so to study. Work on whatever it is you need to work on. I don't care. Like, if you want to go home early for lunch, that's fine too. I am a big believer that time is supposed to be spent on what you guys want to spend it on. So let me know how I can help. I'll say that a lot. If you need help, I'm here. If you don't need help, that's fine too. So work on something, or let me know and you can go. I do need your form. If you don't have your form, I can't let you go.